Right now, as you're tuning into this explainer, you are, technically speaking, living through an ice age. I know, it probably isn't snowing outside your window right now, but geologically, our planet is completely locked in a massive, planetary-scale freeze. Today, we're going to look at the mind-bending forces that have repeatedly turned our home into a frozen wasteland, and exactly how life, which includes us by the way, managed to survive it.
I know it sounds totally counterintuitive. You're probably thinking, wait, are we really in an ice age right now? And the answer is a definitive, absolute yes. We are literally sitting in one of the coldest periods our planet has experienced in the last 500 million years. You see, Earth's climate is basically a giant swinging pendulum. So to really understand where we are today, we have to look way back at our planet's deep time heartbeat.
Okay, let's clear up a major misconception right off the bat. An ice age is not just a brief, intense period of snow. Technically, it's an incredibly long stretch of time. We're talking tens of millions of years, where average global temperatures drop just enough for massive polar ice sheets to form. So think of an ice age as a long global season. And within that massive season, the actual weather swings back and forth between colder glacials and milder interglacials. To help visualize this, here is our 2.4 billion year roadmap. We're going to take a quick journey through deep time and explore the 5 major geological periods where Earth essentially froze over. We'll start 2.4 billion years ago, hit the 720, 450, and 360 million year marks, and then finally arrive at the 34 million year mark, which happens to be the ice age we are in right now.
Stop number 1 on our timeline, the Huronian Ice Age, 2.4 billion years ago.
This one is wild because it happened way before there were animals or plants on land, and the culprit was entirely microscopic. Early life actually triggered this deep freeze. Back then, Earth's atmosphere was heavily blanketed in warming methane. But then, these tiny ocean cyanobacteria figured out how to do photosynthesis. They just started pumping out vast amounts of oxygen, which reacted with the methane and completely destroyed it. Without that methane trapping the heat, the greenhouse effect just crashed. Earth plunged into a deep freeze for almost 300 million years. So the very organisms that eventually allowed us to breathe actually nearly froze the planet solid as a byproduct.
All right, fast forward over 1 billion years to stop number 2, the Cryogenian period, or as it's famously known, Snowball Earth.
During this period, the entire planet, literally from pole to pole, froze into a giant ball of ice. To really wrap your head around how extreme this was, geologists have actually found ancient glacial deposits in rocks that were sitting squarely at the equator at the time. Finding glacial deposits at the equator is basically like finding snow-plowed tire tracks in the dead center of the Sahara Desert. It means if you were standing on the equator back then, you wouldn't be in a jungle, you'd be standing on a solid glacier.
So how on earth did we escape this planetary prison? Well, volcanoes. They just kept erupting underneath that miles-thick frozen shell, steadily pumping out carbon dioxide. And because everything was completely frozen over, that CO2 couldn't be absorbed back into the ocean or rocks. It had nowhere to go. It just built up and built up in the atmosphere for millions of years until a greenhouse effect became a massive pressure cooker that violently melted the ice shell. And actually, this chaotic freeze and thaw cycle is likely what kickstarted the evolution of complex multicellular life.
Moving right along to number 3. The Andean-Saharan Ice Age, about 450 million years ago.
At this time, parts of South America and Africa were clustered near the South Pole in an ancient supercontinent, and this freeze directly aligns with the Ordovician-Silurian extinction, a devastating die-off of marine species. The trigger for this one? The rise of the very first land plants. As these plants spread like wildfire across the continents, they acted like a giant vacuum, sucking massive amounts of carbon right out of the air and plummeting global temperatures. Once again, life itself messed with the climate thermostat, and it had deadly consequences.
Next up is number 4, the Karoo Ice Age, roughly 360 million years ago. This was an absolute marathon, affecting the southern supercontinent for over 100 million years. This era is a brilliant example of geological cause and effect. A massive explosion of plant life created these enormous, giant, swampy forests that just soaked up atmospheric carbon dioxide, cooling the entire planet down. But here is the truly mind-blowing part. Those exact same ancient swamp forests eventually died, got buried deep underground, and turned into the very coal deposits that human beings are actively mining and burning today. Talk about things coming full circle, right?
Finally, we arrive at number 5. The Late Cenozoic Ice Age, which kicked off 34 million years ago.
This is the one that really matters to us because, as I said at the very beginning, it's still going on right now. So what triggered our current ice age? It all comes down to continental shifts. Antarctica actually separated from South America and Australia. When it broke away, it opened up a brand new ocean current that just continuously circled the entire Antarctic continent. This completely blocked warmer waters from reaching it, effectively trapping Antarctica in a thermal deep freeze. For the first time, a massive, permanent ice sheet was able to form.
Now, if we drop down to 2.58 million years ago, things get really intense. We enter the famous Pleistocene epoch. This is when massive sheets of ice, we are talking over 2 miles thick, began relentlessly advancing and retreating, literally burying huge swaths of North America and Europe. In this absolutely brutal, freezing environment, only the toughest beasts survived, which drove the evolution of iconic megafauna like woolly mammoths and saber-toothed cats.
But why did those ice sheets repeatedly creep down and then retreat dozens of times over the last 2.5 million years? Well, the answer lies in something called Milankovitch cycles. Basically, these are just incredibly subtle, chaotic wobbles and shifts in Earth's orbit around the Sun. Over tens of thousands of years, these tiny little wobbles subtly change exactly how much sunlight hits different parts of the planet. They are essentially the pacemaker for that back-and-forth pendulum of advancing ice.
Okay, I really want you to burn this exact number into your memory, 11,700. Because 11,700 years ago marks an incredibly critical transition in our planet's history, and it is absolutely crucial for our own species. That number marks the beginning of the Holocene. It's essentially a brief, warm, interglacial breathing room phase, and what most people don't fully appreciate is that literally all of human civilization, agriculture, the very first cities, the invention of writing, all of it, happened entirely during this one single, relatively stable slice of an ice age that is still ongoing. The very fact that massive ice sheets still cover Antarctica and Greenland today is the clearest sign possible that we never actually left the Late Cenozoic Ice Age. We're just enjoying a nice warm summer within it. When you zoom out and look at this entire 2.4 billion year story, a really profound pattern emerges. Ice ages, they aren't just random strokes of cosmic bad luck. They are driven by a recurring checklist of massive planetary triggers. Huge shifts in greenhouse gases, continental drift, reroute in ocean currents, and, fascinatingly, biological life itself, dramatically reshaping the atmosphere.
But here is the truly amazing takeaway. Despite total planetary freezes and absolutely devastating mass extinctions, the Earth's climate is a swinging pendulum. It has this incredible, almost stubborn ability to recover, thaw out, and just keep going. The climate has always been changing, constantly driven by forces far, far bigger than any single species. Which leaves us with a final, absolutely vital question. What does deep time teach us about our current climate pendulum? Because while the Earth as a rock has always survived these massive freezes and thaws, the species living on it often face devastating consequences when things shift too fast. Understanding exactly how and why Earth's climate shifted in the ancient past isn't just fun geological trivia. It is genuinely our absolute best tool for surviving the climate shifts happening around us right now and predicting exactly where this giant planetary pendulum is going to swing next.